Hello world, your variables are lying about where they live. Some of them die the moment the function ends. Some live until you delete them. Some never get deleted. The difference between them is the difference between a program that works and a program that crashes. Today we open your computer's memory and look inside.
When your program runs, your computer gives it a chunk of RAM, memory, a scratchpad. Everything your program does, every variable you create, every object you build, every list you grow, has to live somewhere inside that scratchpad. But here's what most programmers never learn. That RAM isn't one big space. It's split into two completely different zones, with completely different rules. One zone is fast, organized and disciplined. It cleans up after itself. The other is enormous, flexible and chaotic. It cleans up only when you ask. These two zones have names every senior engineer knows by heart: the stack and the heap.
Almost every Python tutorial or C tutorial skips this. They show you how to declare a variable, but they never tell you where it goes. So today, we don't skip it. We open both doors.
Picture a stack of plates in a cafeteria. New plate goes on top. When someone needs one, they take from the top. You never reach into the middle of the stack. You never pull from the bottom. Top in, top out. Always. That's exactly how the stack zone works. When your program calls a function, the stack gets a new plate. That plate holds all the local variables that function needs. When the function ends, the entire plate is removed. Every variable on it disappears with it. This is why your local variables die when a function returns. They're not deleted by some cleanup routine. They were on a plate, the plate was thrown away, they went with it. The stack is fast because the rule is simple. Only the top changes. The CPU keeps a single pointer to the top of the stack and moves it up or down. No searching, no bookkeeping, just push and pop. But the stack has one weakness. It's small. Usually only a few megabytes. If you push too much onto it, the program dies instantly. With a name everyone fears: Stack Overflow. Now, the other zone, the heap. If the stack is a stack of plates, the heap is a warehouse, a huge open space. You can put anything anywhere. Big things, small things, short-lived things, things that need to live for hours. When you create something on the heap, you ask the system for a slot. The system finds an empty space big enough, hands you back the address, and your data lives there, independent of any function, independent of any plate. This is the magic of the heap. Things you put there outlive the function that created them. Your photo loaded into memory, your machine learning model, your list of 1 million users. All of it lives in the heap because it has to survive longer than any single function call. But the heap has its own price. It's slower than the stack. Finding an empty slot takes work, and it doesn't clean up after itself. If you forget to release something on the heap, it just sits there, taking up space forever, until your program ends or until it eats all your RAM and crashes. That's a memory leak, and it's the most common bug in C and C++ history.
As you can see, this is C, not Python. Python hides memory, C doesn't. If we want to actually see where variables live, we need to come down here. This first line imports the standard input-output library. Same idea as Python's import. We're bringing in tools we need, in this case, the ability to print to the terminal. Here's our function. Void means it returns nothing, like a Python function that returns none. Its only job is to create a variable and show us where it lives. Int x equals 42. In Python, you would just write x equals 42 and Python figures out the type. In C, you have to declare it yourself. Int means integer. This variable gets created on the stack right now at this line. The CPU sets aside a slot in the stack memory, puts 42 in it. That and x with the ampersand, that's C for give me the memory address for x, not the value, the location, the slot number in RAM. And down here in main, we call the same function 3 times, same function 3 calls. Watch the address does each time. Let's compile and run. Let's say gcc stack underscore demo.c dash o stack underscore demo stack demo. 3 calls, 3 identical addresses. Every time the function ran, the variable x got the same exact slot in the memory, because when the function ended, that slot was freed. The next call got it back. The variable truly died at the end of each call, and the next one was born in the same place. Now, let's go to the heap. Same idea, completely different behavior. We have a second include this time. That's where malloc and free live, the tools for manually managing heap memory. The function signature changed. See the asterisk? Int asterisk means functions, this function returns a pointer, a memory address, not a value, an address. Because the thing we're creating lives in the heap, and we need to hand back its location so we can find it later. This is the key line. malloc memory allocate. We're going to the heap and saying give me a slot big enough for one integer. Size of int tells it exactly how many bytes we need, usually 4. malloc finds an empty space in the heap, reserves it, and gives us back the address. The asterisk here means nothing different. X holds the address. Asterisk x means go to that address and put 42 there. X is in the box number. Asterisk x is what's inside the box. And we return x, the address. The function is about to end, but the heap slot isn't going anywhere. We're just handling the address to whoever called us. Down here, after all 3 functions have finished running, we still print the values. Asterisk a, asterisk b, asterisk c. Those functions are gone, but their heap objects are still alive. And these 3 free calls at the end, this is us giving the memory back. Every malloc needs a free. Without this, these slots sits in the heap forever, taking up space until the program ends. That's a memory leak. Let's head back to the terminal now and say gcc heap_demo.c-o heap_demo. And then let's say right here heap_demo. 3 different addresses this time. Every malloc find a new slot. They're not reusing the same space. The heap doesn't work like the stack. It's a warehouse, not a plate dispenser. And look at the last line. Still alive. The functions ended, but the values didn't disappear. They're sitting in the heap, waiting right where we left them. That is the difference. Stack variables die with their function. Heap objects survive until you free them. Okay, last one. This is the one I want you to watch carefully. Let's go to the overflow and let's clear the terminal. This function does one thing. It calls itself. Every time it runs, it prints the current depth, then calls itself again with depth plus 1. No condition, no escape. It will never stop on its own. This line right here, this is the problem. Every call to this function adds a new frame to the stack. And this line means there will always be another call. The stack grows and grows and grows. We start with depth 1 in main. That's all it takes. Let's go to the terminal now. Let's say gcc overflow.c-o and overflow. Alright, let's say right here again, overflow. And as you can see, watch the depth counter. The stack limit is filling up frame by frame, thousands of times a second. 261,000 calls. Then the stack ran out of space. The program tried to go further and Linux killed it instantly. Segmentation fault. Memory boundary crossed. That's a stack overflow. The stack is small, a few megabytes. Fill it up and program dies. No warning, no recovery, just death. Every recursive function needs a base case, not as a style preference, as a survival requirement. Without it, you're writing a program that will eventually kill itself. They even named a website after this error. It's popular. You've probably used it.
Now you understand the 2 zones. Let's see why this matters in real software. When you write a function that calls itself, recursion, every call adds the plate to the stack. If your recursion has no escape, the plates keep piling up. The stack fills, the stack overflows. The program dies. That's why every recursive function needs a base case. It's not style, it's not preference, it's the line of code that prevents your stack from collapsing. Memory leaks are the heaps version of the same problem. You ask for a slot, you use it, you forget to give it back. You ask for another one, you forget that one too. Hours pass, your RAM fills, your laptop fan screams. Eventually, the system runs out of room and kills your program. In Python, you don't have to deal with this directly. Python has a garbage collector that watches the heap and removes things you stop using. But that garbage collector costs time. Every few seconds, your Python program pauses to let it run. Languages like C, C++, Rust give you more control, but require you to remember every slot you took.
2 zones, 2 contracts. Every program you've ever run uses both. And every AI model, it lives in the heap. The biggest and hungriest objects in computing. GPT, Gemini, Llama. Gigabytes and gigabytes of model weights sitting in the heap memory, surviving every function call that touches them. That's why an 8GB laptop can't run a 20GB model. It's not about your CPU. It's about your GPU. It's about whether the heap has room. Memory isn't just storage. It is geography. And once you know the map, the rest of computer science gets easier. Next video, we go up one more floor. The operating system. The thing that decides which program gets memory and which programs don't. If this video changed how you think about your code, then hit subscribe. I'm Hex1000, logic behind the code, signing out.